Hello, everyone. Welcome to the expert panel that we have today. I have with me the panelists, but I'm going to start the session today with an introduction to the Revolution in Simulation Community Initiative. The RefSim initiative was launched at the NAFEM's CASE conference in 2018. It's a free web portal that gathers together in one online space all of the resources that you might need to take your simulation investments to the next level. It focuses on next-gen simulation usage, keeping your organization at a point where you can maximize the impact of simulation on your business goals. The case studies section of the online website are an important resource that is available in this portal. We've gathered over 350 interesting cases, and that list is constantly growing, and we keep it up to date. You can find out what your industry peers are doing to increase the impact of simulation in their organizations. So please join the community and contribute your own success stories. A number of industry leaders have volunteered their expertise, knowledge, and time to be moderators of a growing list of topics of interest. They curate freely available materials and reference them on the different topic pages. You see the various titles there on the slide. You can access these under the Cutting Edge Simulation menu on the main page. And you can ask questions and start discussions with the moderators. Please go ahead and contribute your thoughts and materials to share with the community. Now, with the help of the moderators and our community, we have gathered a trove of resources, over 1,400, and continue to grow. You can access these under the Resources tab. Very few of these are actually stored on the site. The site itself provides a short summary of a resource and then points to its original location on the web. Please contribute resources that you think would be valuable to the simulation community. Now, RefSim has a growing list of more than 20 sponsors, industry thought leaders that are an integral part of this revolution. The sponsors provide more than just financial resources to the community and are critical to the ongoing success of the initiative. The online platform regularly has over 2,000 visitor sessions a month and over 5,000 members and followers, all with a particular interest in next generation simulation usage. If you're a simulation provider at the cutting edge of simulation, please join us at refsim.org and contribute to the community. Starting in 2004, RefSim and SimData will be curating and hosting a year-long series of events and resources focused on the AI ML in simulation topic area. We've seen from the first two introductory panels on this topic, including this one, that there is huge interest on this topic in the community. Stay tuned for details on how you can sign up for this useful, informative, and educational series on this exciting new topic in the simulation space. Today's moderator, Justin Hodges, is a senior AI ML technical specialist at Siemens. He helps customers solve relevant problems which add value to their business and their products. Justin earned his PhD in mechanical engineering in the area of thermal fluids and has a passion for AI and ML. Hence, he's here. His doctoral research involved the prediction of turbulence and thermal fluids using advanced turbulence modeling and machine learning approaches. Justin is in the process of actually releasing a book on this topic. It's a how-to book for those in the simulation world that want to learn more about how to apply ML. He wrote it after countless projects where he had to teach the same steps over and over again to educate people that are experts in simulation but new to ML. And you can sign up to receive more information on the book using the QR code that you see on the screen. So with that, I'd like to turn it over to Justin.
Thank you, Malcolm. It's a pleasure to be here, and part of the reason it's such a distinct pleasure in this specific scenario with this discussion we're going to have here is that I had the pleasure of meeting both of the presenters organically through academic and industrial collaborations and crossing paths. And I'm just really pleased to be able to have this discussion with you all. So with that, it'd be great to start with introductions. Maybe we can go with you first, Astrid, to introduce yourself.
Yes, sure. So yeah, first of all, yeah, thanks for having me, Justin. Thanks for reaching out. So my background is in mechanical engineering with a PhD in scientific computing and CFD. And actually, most of my professional experience I gathered while working at Siemens, previously now Siemens Energy. So I spent 5 years in the aeromechanics methods development department. And so mainly also there, apart from developing tools and software around aeromechanics, I was working on multidisciplinary optimization and surrogate modeling. Then actually a few years ago, I left Siemens and went a bit more into the direction of data science, and machine learning was a cool thing at that time. So I thought, okay, I jump onto this. And so then I gathered a few external experiences. I worked for Vattenfall, Rolls-Royce, Neural Concept, also ran my own business for some time. And then actually earlier this year, I rejoined Siemens Energy, and now I'm part of the team around tools and data applications. And I feel that there now I really can also further continue my passion and working at the interface between engineering and data science. And yeah, so actually also one of the projects I'm actively working on currently is really the layout and the design of data models, especially for simulation data.
Wow, that's great. With pleasure now, I'd like to ask you to introduce yourself, Simon, to everybody.
Yeah, so my name is Simon Xu. I work at General Motors as a tech fellow. It's my current position for vehicle optimization and machine learning. This is in the GM Tech Center in Warren, Michigan, and our organization is called Engineering Design Virtual Integration. This is a new organization that has been just formed. So I also chair the GM Global Optimization Focus Group. That focus group is responsible for innovations in all technologies, optimization, machine learning in vehicles and electrification propulsion system development. So my background has been same as everyone, mechanical engineering, aerospace, and engineering mechanics. And I've been working in this field, and especially focused on optimization for many years. And previously we were focusing on MDO and optimization to lightweighting the vehicle. That was many years ago because of CO2 challenges, but now with the electrifications. So we are working on now battery systems, vehicle design architectures, and CFDs, try to get the range and so forth. So machine learning is a natural extension recently to that optimization. So I would like to make sure that the two are kind of coupled going forward as versus independently. So this is a really natural thing that we were focusing on this. And even though we have done a lot more work in the optimizing, I feel like machine learning could be another disruptive technology that can revolutionary nice what we are doing in these areas.
That's great. So I think what's clear now after introductions is that this will be a great discussion from our presenters on actual real life experience, plus, you know, of course, competencies on the core technologies area and this knowledge in general machine learning. This won't be a sort of buzzword type discussion about possibilities. It's really coming from practical experiences and practical knowledge over many years from our distinguished presenters. So with that, we can engage in that discussion immediately. Maybe we can follow with Astrid to go first and give a bit of an overview of what she wants to talk about and share about her experiences and focus areas. So with that, I'd be delighted to pass it to you, Astrid.
Sure. Just let me know when you can see my screen.
We can see.
Okay, perfect. So actually, yeah, just at first, I just want to share real briefly what Siemens Energy is doing. So I mean, the overall portfolio is super huge, and it's also moving more and more towards the decarbonization. So we do have electrolyzers, wind power, all of this. So what we can see now here is just a small excerpt, so to say, really just from the gas service business unit where I'm part of. So yeah, as you can see, we do build products for power generation ranging from the really large gas turbines to generators. And so my team is actually part of the large gas turbine engineering. And so to transition a bit already into the data topic, and also to probably motivate a bit the digital twin buzzword topic, I just want to show you that that we do have yeah, lots and lots of data. Oops, that was, I don't know why this happened. So basically, I think just all what I want to say with this is, so Siemens Energy, so we are not a software company. So we do develop software, but mainly for internal use. So we do not sell software, but what we do have unbelievable amounts of data. And actually also what you can see here, so in this in the small box under data processing, which shows that yeah, whether gigabytes of data processed per day and historical data available, that's actually just for the, let's say, the normal, the usual instrumentation. But apart from this, we do have unbelievable amounts of data coming from heavy instrumented machines. So when we now yeah, really delve into this machine learning and simulation, so there we, yeah, I think we just have different areas of application. And so all of these areas, at least for us, they also heavily connected to each other. And in the best case, then they can all be united and also fed from the same models. So of course, we do have the time to market use case. So to be able to front load design decisions, make these decisions earlier in the product development process, make iterations faster in optimization. Then we also have the digital twin use case. So yeah, as I just showed you, we do collect lots of data. And so when you now just imagine with the right models in place, you're actually able to do yeah, or to receive and to do real live predictions with the actual boundary conditions measured in the field. And yeah, so that's just something where we'll also show you a bit later on how we actually use this. And then we also have this use case of assessing deviations. Because if the parts are actually manufactured, they are not exactly as we designed them. And yeah, with this, we are able to, for example, then really take the measured geometry of the manufactured parts and get predictions for the part as it is now. So now I just want to go through each of these three use cases real quick. So as I said, with the time to market, essentially what I can say is that the 0D surrogate modeling, it's super well established. We do this all of the time. So every part we design, we run optimization, we perform the surrogate modeling, we augment at least one or multiple or even the whole process chain with these models. So that's pretty well established. But now we are, of course, dive more and more into the higher dimensionalities for these kind of surrogate models. Yeah, and then of course for all kinds of different applications. And essentially, I just want to give some examples for which of these parts we apply these surrogate modeling techniques. Of course, compressor, turbine, combustion systems, and then all of the different disciplines you can think of, ranging from mechanical integrity to aero, heat transfer, so like everything. So then, as I said, the topic of digital twins. So here it's really that for each part, we know exactly in what unit these parts are installed. And so for these units, we acquire measurement data. And with this data, which actually then reflects the real boundary conditions in terms of temperatures, operating conditions, how much time has been spent already, we are able to run predictions while the unit is running, and we are able to predict the lifetime actually of these parts for our entire fleet, basically. So these models, which are currently used, it's also models coming from simulations, but also mainly for 0D, 1D, and 2D. So there's also still some more dimensionality to endeavor. And then for the deviations assessing, so there's also very, very important to understand, or why is this such a big issue? Because as I would assume it is for main companies, we do still rely on parameter-based design and CAD models. So then even when we receive the real geometry, the real measured geometry of a manufactured part, we are not able to feed this directly into our design process and to run the same kind of simulations and calculations on this, because it does not reflect this kind of parameter-based design, and the scanned geometry cannot be translated exactly into this kind of parameter-based design representation. So here it's really important for us to get away from these parameters and to come to a parameter-free presentation and a parameter-free model, which can actually digest the geometry directly and run predictions on this. So with this, I'm already almost at the end of this kind of introduction and motivation. And here I just want to share some of the challenges we actually see every day and we come across. So I think really important is people. So we need to upskill people if we want to use these new techs and methods, because they also need to understand the limitations of this, and they also need to leverage or level their expectations to what is actually possible. So there's a lot of change management, explaining, upskilling, and then we have a huge topic around data. So how is it stored? Where is it stored? And can we store all the data we want to store? Because it needs to be compressed. How can we do access control? What data models do we need in place? And and then actually we are already coming into the challenges around ML ops, because as I said already in the design optimization, the use of surrogate models is already well established. But already there, we do see that we need proper processes in place to allow for model retraining and updating of these models and data sources.
This is a great slide here. I get this question a lot, as I'm sure you do, for people early in their career asking what directions and competencies to focus on. Well, here's your heat map, right? And I think what's very interesting is that the barrier between computer science and mechanical engineering is becoming really, really thin right now, at least in this area here with ML ops and data. So I think this is a great one here. I'll make one comment and then I'll briefly try to transition to just one question. So the comment is really related to the wealth of experience that you're sharing pretty succinctly in your slides, because you've said things like the 0D modeling approach and that stuff like that with surrogates is already well established. Then you had another slide that said how the value opportunity is really in the fact that you can front load with these surrogates. So for companies that are early in adoption and considering adding in machine learning into their CAE way of doing things and testing, I mean, I think that's one of your first steps, right? This is a very known, established, possible thing to get into with these lower order surrogates. You don't need fully high dimensional spatial and time resolving surrogates to get started. You should focus on integrating the 0D for these early predictions, because this directional insight early on is still very, very valuable to the overall way that you can expedite your projects.
Yeah,
so
yeah,
now,
and actually, if I just can add on this, because what then comes alongside with this is if you because you need to have a lot of process and infrastructure in place to even just allow for the 0-day surrogate modeling. And if you have reached this this maturity that you are able to train a surrogate model, I mean, that's just like the last bit of sugar coating on top. But before that, you can even do so much more with this. I mean, if you have this data set, this curated data set, then that's your treasure. You can do sensitivity analysis, you can do great visualization. So all of the stuff then basically comes for free. And then the modeling, the surrogate models is just, like the cherry on top.
That's a great part to end on here as we transition to our other presenter here. So Simon, you're welcome to go over your use case and sort of beginning part of the presentation whenever you're ready. Thank you so much, Astrid.
Okay, can you hear me?
Yes, sir.
I'll try to find the button that I can share. It seemed to be going away. Let me see. Okay, got it. Let me know if you can see my title slide.
You're good.
Okay, thank you. So you can see this title here. I put a title here. This is more like a panel discussion, but really we try to discuss the forward thinking of how to shape our tomorrow's strategies in using AI ML. And so first, good morning. I'd like to dive into the motivations, why we want to use AI ML to integrate and reshape our virtual processes. There's a couple areas I want to emphasize and focus on. And one is enhanced design assessment. The predictive model, as Astrid has shown, is very powerful that can be developed to correlate usually a design element or design parameters with that of performance metric. And if we have this capability, then this insight can allow us to tackle previous unsolvable problems. So the linkage could be between the simulation and the outcome, or it could be a testing to the outcome. So a lot of time, the underlying physics are not so complex that we will not be able to understand completely. So this deeper connection can be uncovered through this parametric link and correlations. So it's possible to solve unsolvable problems or in hard to define problems. We actually have seen cases like this in GM that seem to be pretty successful. The second thing I want to focus on is accelerating the iteration cycle. With these tools, this could be a reality that the speed of the AI would allow us to interactively iterate in the design almost interactively, and then pinpoint modification that yield the significant improvement, which enable us to iterate quicker and more effectively. And the third one and fourth one I think is even more interesting is the generative design capabilities. So right now the design was generated mostly by person and people. If we be able to leverage and harness this power that using AI, we can explore a wide range of design spaces or design alternatives that we wouldn't be able to do because the limitation of resource, imagination, whatever you have, which allow us to uncover unique and efficient designs that push the boundary of innovation. And lastly, it's not least, is the cross-functional optimization that I think is very powerful, that we already have tools that can, and linking different disciplines with AI, that we will be able to do this much faster and more thoroughly. And so that we can optimize design across various functions much faster and ahead of the market with groundbreaking product. So on the right, I want to focus your attention now, getting into detail, is these are the potential benefit the technology can bring. And things we try to focus on sustaining technology, which means that we want to actually improve the product by enhancing features and operational efficiencies, not changing anything, but make it better. But so it's more valuable to the customer. But better yet, the radical technologies. And these are the ones that drive the creation of novel product that actually carve out new markets, basically a new product that has not been imagined before. So that will bring up fresh customer base with a different segment. The thing that we want to look out for, or even more excited about, is disruptive technology, because when the AI machine learning disrupt the industry, they can alter the fabric of the market. And for example, if democratize the technology, make solution more affordable, accessible, or sometimes paradigm shift of the product that redefine the customer's expectations, often displacing established market leaders and realign industry standard. So I just want to show maybe two case studies here that GM has embarked. It's not exhaustive. We are doing a lot more than this. So first problem is the rapid aerodynamic development with AI machine learning. So here's the approach. What we have done is starting with a very comprehensive DOE study, which utilizing power flow models, real CFD models, to thoroughly investigating the entire range of vehicle styling possibilities. What we mean that is the picture shows that you can see there, there's a number of variations that change the vehicle size, dimensions, length, width, height, angles, and small, large, medium, so that we actually expand the possibilities into capture all the possible design parameters. And then we can use a deep learning network to train on this extensive data set with a powerful analytical tools. Then we tune the parameters or hyperparameter to make sure that the prediction is the best we could. So the result is that once we have the model trained, we find actually this model is sufficiently reliable as a predictive model, comparable to that of a full-scale CFD by few counts in terms of CFD. And because of that, it's highly effective for styling concept selections and iterations. What do we mean by that is there's a lot of new ideas when the styling studio will come and they have maybe different concept they want to evaluate quickly. And typically it takes weeks for us to respond on a CAE point of view, because you need to get the surface, match it, and model it, make sure the element is correct, and submit the job and debugging the problem if there's any, and interpret the results, and maybe sometimes do some what-if studies to see what will be the improvement or suggestions. With this model, we will be able to do this almost interactively, but I would say give or take 1 or 2 days. The reason is we want to make sure the model matches well, and also the result is meaningful, so we can do some studies. So this become really a culmination of the work that actually make React and become a cornerstone of the design team, which can significantly streamline the selection refinement, like I said, the styling product. And the third point here, I was saying that because the underlying linking between the machine learning model and the CFD models, the full-scale CFD model, are done through parameters, then we have a chance to actually optimize the solution with a much faster model. This is the step here. So we have the model, we can do what-if studies and optimizations. Once you actually have the final model that you're happy with, or models that you're happy with, then you can go back actually quickly realizing the model in the full-scale CFD model and run a verification run. So then this new result can actually be fed back into the database, so that you have a new anchor point that are considered optimal in So over the years of iterations, eventually you can actually enrich the model base and with new designs that feed into it. Maybe your new design has changed and then the model base can be skewed towards the new styling changes. So next I want to focus on maybe some of the challenges that we run into and how do we solve it. Number one is that we find actually it's very hard to fit all the body style into one model, because body style in here means car versus trucks, for example. And the second issue that we notice is that because we have vehicles that have different brand characteristics, so maybe underlying the same size of vehicle, one is a Chevy, the other one's a Cadillac, it has different embellishment, if you will, or styling changes or cues that make the product distinguishable. And as a result, it's very hard to capture all these parameters in the comprehensively in the machine learning model, because these features is magnitude order or couple magnitude order more complex than the shape of the vehicle. So the solution we come up with is, first we have to separate the machine learning model for different type of vehicle body styles, and we found that after we've done that, and there is a huge improvement in terms of the accuracy of the model, so that we can work with a car's architecture that's distinguished from the truck, and so on and so forth. The second solution we come up with to the challenge is the building a generic model which are free of embellishment to capture the main theme. So here we actually have a base model that without the complex design details, basically it's a clean model that's kind of a no-frill model that capturing the core theme, and a model serves as a foundation upon which you can layer the impact of intricate details through a separate study. So going from coarse to fine. And the separate study currently is done still by person, but it reduces the amount of work that CFD engineer which has to do today, which is chasing out the styling surfaces. So we can add the two together. And so as a result, with these strategies, we're paving the way for AI and machine learning to not just complement, but enhance our design capabilities. Going to another example here is the objective here is to focus on enhancing HVAC design through predictive analysis of vehicle cabin thermal comfort. Before we dive into detail, I want to acknowledge that my colleague Alok Wary, and who might be in the audience, is the champion for this study, and along with a few folks from Siemens, Michael Cruz and Ganesh, who might be also joining this, and I welcome if they are here. So here are the challenges. Basically, we have a complex task of addressing asymmetrical and transient thermal condition within the vehicle cabin. Because imagine the person sitting in the vehicle, they have different heat that are coming from different sources to try to warm it up, but it's not in an ideal, like an empty room kind of, because all the components in the vehicle. So they first developed a measure with which you can actually effectively measure the comfort level of the person. But the goal here is to try to minimize the energy usages so that the heat is going to the right place. And that's the optimization problem they are facing with. So in order to do that, they have to balance different environmental and vehicular factors that impact the comfort. So here in the study, there's 37 distinctive features that being developed, including environmental conditions, glazing properties, which are the window, windshield, and the windows, and these are properties that we can put in, and HVAC settings on how to direct the heat sources to different persons in the different sitting in the different seats. So a total of 37 parameters and 241 CFD simulations to train the model. Plus there are 50 simulations reserved for testing purposes to make sure the model is fully functional. Since this is not a simple optimization problem, this is the training the model. We want to have a comprehensive model that can capture all the features and details. And then 3 machine learning techniques were compared as a study purposes. Linear regression, random forest, and ANN, artificial neural networks. And then hyperparameter were tuned and to get the model to work as fast as possible. ANN is a schematic presented here, and random forest is a complete different method that actually can also producing results working on discrete values. And so it's being studied. So the key finding is that AIM performed the best. And it's very encouraging that, that we will be able to get or demonstrate less than 5% error rate to the forecasting number, which we call EHT, equivalent homogeneous temperature, which is the benchmark for how confident the people is that developed as part of the project or prior to this project. So here, actually, we have a model that can be used and effectively to help the design in real time. Because, you know, the CFD results, again, is taking hours, if not days, to produce and weeks to prepare. And this model will give you the answers almost instantaneously. So potentially, these tools enable our EV design approach, especially now because the energy loss from the cabin cooling is a big deal in the winter. For the EV designs, we want to efficiently using only the heat that needed or necessary to get the people to be comfortable, so we can maximize the range. So you can see by using AI/ML, we aim to revolutionary product development process, given the new challenges, which help us identify optimal design faster, assess their pros and cons, and generate novel designs that outpace competitors. So I will stop here to see if any question.
I have two, but I think maybe for the time structure of the agenda, what we can do is I'll reserve those two questions for the conclusion of the webinar at the very end in the last 10 minutes. And then at this moment, we can transition to the next set of questions and panel discussion where Astrid will kick off if you wanted to do so. So the next section here,
Justin,
I think there's a lot.
Pardon me for interrupting. I just wanted to let people know who are listening that they should enter their questions into the question panel. We forgot to mention that, and then the panelists will be addressing some of those at the end of this event. Thank you.
Perfect. That's a great comment. I see about 6 questions so far. So with that now, like I said, we'll transition to the next block. What we're going to do is just have a discussion with no slides shared, just a conversational thing. We'll have Astrid go first. And I think one of the key things to really get the most out of the presenters here and sharing is the fact that a lot of people are interested in getting started, whether they're students looking for a career direction or whether it's companies of simulation and testing practitioners that are experts in the domain area who want to integrate more machine learning. I think that either way, we could really benefit from, like you had on your final slide, Astrid, one of the bigger blocks was people and upskilling. So this will be a portion here where we just ask both of you, since you've done years now of building up experiences and accomplishments professionally in machine learning from your formerly mechanical and aerospace more traditional background. So what advice would you have for beginners to get started, get enabled, key things that were really good for you or resources that are present that you would recommend to them at this time?
Okay, yeah. So then I will start, and there I basically just can thank you for giving me the opportunity, because it fits this question and this topic so well to actually advertise one community I came across a few years ago, and I'm now part of the organization committee. So there's one community, and mainly every year now there's a one year pause. There is an event which is called the Automotive CFD Prediction Workshop, and I think actually that especially to this community, which is addressed now with this webinar today, this is interesting in general, because yeah, it's also about simulation, so probably a lot of CFD people out there. So the initial motivation for this workshop was really that it's a joint effort in finding best practices. So until last year, the usual process has been that participants who are, basically people who sign up and say, okay, I'm willing to contribute. They receive a geometry, a mesh, ready to use, a case description with a fully defined set of boundary conditions. So essentially the case is set, you get the mesh, and then everything what participants need to do is to solve this case with his or her choice of software and solver settings. And the intent behind this is that, of course, everyone will try to solve this case as best as possible to his or her knowledge. So we'll apply already best practices. And then afterwards, when all the participants have actually submitted their results, then these results can be compared against each other and also against test data, measurement data. And so by this, it's really a community effort. It's not about blaming people. It's also for testing different methods. So I think the traditional thing would be to test different turbulence models, time step sizes, all stuff like this. Test new methods, get a benchmark, also test how my method or my approach does actually compare to the community. So it's a great thing, I think, because you can test yourself, you get in touch with a lot of people. So then actually, so why am I telling all of this? Because then last year when I was working at Neural Concept there, I submitted a 3D prediction instead of a CFD result. And so last year this has been the only submission as such, but then we actually decided, as we do see that it's becoming a huge topic, and a lot of people are looking into this. So we decided to do a technical focus group, especially around AI and ML techniques for CFD. And so the next workshop, which will take place the next year, will have actually a lot of participants who are willing to contribute, especially in this sector. And now, with all of this being said, now the real nice part about this is that we as the organizers of this group, we will provide a very comprehensive data set based on the Drive Air case, which is a known, well-known benchmark case in the automotive community. So we will provide a very comprehensive data set to all the participants, consisting of multiple hundreds CFD results fully resolved in 3D for different geometry variations. And I think that's actually a really great chance for everyone just to get this kind of data set and to test different methods, really get their hands on to get started without the burden of actually creating this data. Also, after the workshop, the dataset will be published, so then it will be available to everyone. And I think that's really a great place to start, because in order to get started with this machine learning, especially in higher order methods, you need to have the data first, and that's something what is especially I think also for people looking for starting a career in this, it's not really easy, because you do need computational resources to just create the data.
Yes, so we've crossed paths before, but I think this initiative was the one where we spent the majority of the time meeting one another. And I think this is one of the best opportunities for people to learn from, not only because it provides data, but it also provides the models and outcomes and conclusions. So beginners can really go from textbook way of learning to dissecting a problem and then seeing how different people in the community took strides to tackle it. And that is the process of learning, I think.
So of course, what I forgot to say, so to everyone in the audience who thinks now, oh, okay, this sounds interesting, so maybe I might be interested in also participating, please just reach out to me, drop me a message on LinkedIn, and then I'm happy to bring you into this community.
That's excellent. I can't recommend that everyone do exactly that enough. So with that, we'll transition to Simon. So Simon, you have basically 4 or 5 minutes for the same question: advice for beginners, ways for people to get started, even in their companies. I mean, what are some things that you would reflect on and offer everybody on that topic?
Okay. So actually, I have just worked in answering some of these questions you asked. So I have something prepared for this. Let me see if I can share this. So I also get a chance to read on some of the questions. They are very good questions in the panel. We may not have time to cover them, so I try to answer them as we go. Let me know if you can see the slide or it's being blocked or something or not.
We can, and then that's a good point. Regarding questions, we want to leave about 8 minutes for those questions because, like you said, we are getting a lot of them trickling in. So until then, the time is yours.
So I'm going to try to go quick so we can have a chance to maybe answer, and I'll try to answer them as we go forward. So to getting started AI/ML, and people think right away is learning, go back to school. But I think if you are doing the work, for me, the best way is to identify a problem to get solved. So how do we do that? Maybe a lot of people already know what kind of problem they need to solve, but a lot of time it's usually a data intensive task that like a simulation, or maybe it's a testing, or it requires pattern recognitions. Then we need a lot of effort to looking into the details of this to understand what's going on, and things that can benefit from predictive analytics. So also repetitive time-consuming tasks can also be prime candidates. If you can speed it up, a lot of times just the fact that you can speed up. So people ask in the question in the panel that how to convince the upper management. I think if you can convince them that you can save cost or save time, this will be the main drivers. And I've been working this for years on other analytics and optimization topics. This is the one way to get it done. But I think the difficulty usually to start is the data, because AI requires data to train. And if you don't have really data that's organized, that are curated, you will have to spend a lot more time than you imagine to make these data clean, like apple-to-apple comparison, so the machine learning will not get misled by the noises in the data. So quality data, and a lot of engineers actually have those, but usually it takes time to get it cleaned up. And of course, there is the machine learning model. I will just go through a few of this in case people are interested. We are looking into, in previous example, these are AN, it's basic numerical values. But going forward, the convolutional neural network is something that could process in graphics. Recurrent RN can processing time-based data. And autoencoders is something we can use to classify and reduce the problem to features, reduce the dimensions. And then the graph neural network is really great for recognizing or organizing graph structures if you have. So a lot of our simulations actually has 3D images and animations. So these tools we are investigating internally with the help of either softwares or external vendors that looks very promising. And then you have the supervised learning that's really good for label data, or unsupervised learning for clustering and dimensional reductions. The rest is once you started, you want to make sure that the model produces enough accuracy. A lot of time we find actually the project is not completely successful because the model does not produce the right accuracy you need. So you either need to increase your data or you need to actually find a better way to process. So I'll skip the rest. You can read basically continuous improvement and optimization. And I do have one slide on resources that is not comprehensive. And for people who have zero knowledge, they can take the course in Stanford. It's actually free, Coursera, by a professor called Andrew Ng, who is very famous in this field. He's got a couple courses, one for technical people and the other two for intro to technical, but requires some coding background to finish the project or assignment. And then you can get a certificate out of that. And there's also, there are different websites. Fast.ai is a portal for coders. NVIDIA actually have certain courses, IBM's and TensorFlow, which are developers course that are done by Google. So there's a lot of these resources. Astrid also mentioned many that you can get started. So I will stop right here, Justin.
Okay, I'm feeling that these are very endearing recommendations because some of them I've taken personally and can totally agree, especially the one from Stanford. That's really the first one I was exposed to in 2017, and I think it still stands as one of the better resources. Okay, great. So thank you for that. I think everyone's probably feeling very excited to get into those. We have 10 minutes left and we have 21 questions. So I think what I might do, Astrid, if you want to scan for a question that you like to answer, I would say maybe the one at the very top would be good. And while you're doing that, I can open up the floor for Simon and me to pick and choose who wants to answer one of the questions that talked about reduced order models. Let's see if I can find it. Essentially asking if reduced order models were tried because they can incorporate physics and reach also a significant speed up. So Simon, would you like me to answer that one or would you like to go for it?
Yeah, you can actually combine the two when you're working on this. So we actually have other activities try to make a reduced order model using physics. For example, if you have a structure, you can use a beam model to represent that. For CFD, maybe a different representations. And then combine that with that of machine learning, which are trained on large amount of data, and you can actually save time. But the issue is that you need to balance the accuracy versus the speed.
Yeah, and I've had this question, or at least this intersection of the two concepts brought up, and the way I like to think of it is sometimes we know the mathematical form of a physical phenomena we're trying to do, whether it's a boundary layer near a wall or turbulent behavior. Sometimes we do know the form of which it would follow, and our goal is to do things like a regression where we determine the coefficients that would tune the curve to the data. And in that sense, you can still use machine learning models in a similar vein, except now the mathematical form, rather than like say a polynomial or a logarithmic way, it's now much more flexible, because instead of changing these coefficients that maintain the same form, you can change things like the number of layers, the number of neurons. You can have all of these different structures and architectures with machine learning models. And essentially it makes that form much more flexible in terms of the optimization process to determine the best one. And in that sense, that's in part why I believe that it's a very competent approach to take when trying to model such vastly nonlinear relationships over such large data. So in a sense, I wouldn't treat them as completely separate entities. I think that's very much aligned with what Simon said. And with that, hopefully that was enough time. Astrid, did you find one that you like?
Yes, I would actually go with a question about the difference between generative design and topology optimization. So yeah, I mean, from my understanding, topology optimization is really a subset of generative design as such. So, for example, if we now think in a use case which is close to my to my experience, then and we think of cooled blades, which usually would have internal ribs. So then a topical or a typical task for topology optimization would be, for example, changing the number of these ribs. So stuff which is really hard or basically not even possible to do with a classic parameter-based design. But the generative design as such, it's actually much more to this. And from our perspective, the main advantage or chance possibility what generative design brings to us is really that it translates it can translate geometries into another latent parameter space. And by this, it can actually also make all of our legacy designs really accessible and understandable. And we can basically take all of the designs which were created at different times in different design projects. All of these most probably also with different CAD-based parameters. So usually you would not be able to compare these or to translate the part from one parameter space into the other one. But with generative design, we are actually also able to understand and translate all of our also legacy designs into one common generic latent parameter space. And that's actually also yeah, that's a huge chance.
Good. Thank you for answering that. I think the next one, I'll open the floor up to Astrid and Simon to open with this answer. If not, I definitely would have an answer to submit. The question, if I try and find it to read it, it was essentially, are there cases where actual experimental data for training of machine learning models to complement CFD models? Sorry, I read that a little too literally. When should you incorporate CFD and experimental data to supplement? So I'll just provide a generic remark, and then our presenters and experts here will answer. So generally, a lot of times you see scenarios where people take the simulation data, and their whole purpose is that the machine learning model can make predictions that match and are accurate to simulation data. And then you see things like error and loss and accuracy. And in cases where the accuracy could even be 100%, it still could be kind of a misnomer, because we know that simulations aren't 100% accurate. So in the case where we can use different domains to generate data, or different methods like experiment and simulation, then I think that inherently reduces the bias that our final machine learning model would have towards Mother Nature or the true answer. So I would say it's generally a good thing to do in terms of making multiple means of producing a data that you use in your training set to reduce the overall bias. But with that, our other experts here are absolutely welcome to chime in.
Yeah, I actually have a example to answer that question, if I may. This is the area actually machine learning could potentially shine, is that we have certain phenomena in the internal combustion engines that are very complex, and it produces certain noises or certain phenomena that we are not happy with. But it's very hard to simulating all these complex interactions inside the internal combustion engine. And we do have models, but the model does not really correlate very well. So in those cases, we actually collect the experimental data and try to, using all the history that we have on the engine when it performs well or not, and was able to find clues that we wouldn't be able to find just by looking at or using simulations. So this is actually a case where the simulation, maybe the physics was not completely understood, but we can use machine learning to solve a mystery that otherwise is unsolvable.
Yeah, and yeah, but actually, I also just want to add two more things to this. So what I have seen actually also, but that's really let's say on a research case, a model which is really trained with high fidelity measurement data, where the model then actually was able to outperform LES simulations. And yeah, I think this really shows also what you described, Justin, right? I mean, it all depends on the data and the accuracy of the data, what you feed in to the model. But then yeah, this accuracy can then be be gained by the model itself. And yeah, and then of course also another thing is when you think of these approaches where you would try to actually train a model on picking up the difference between low fidelity and high fidelity results. So to use a model to essentially turn a run simulation into an averaged LES simulation. So really to Justin, I think you're on mute.
Thanks, I was. Thank you for the answer. I was just going to say we have under 60 seconds before the slots reached here for the full webinar. I just want to wholeheartedly thank Astrid and Simon to carve out time to do such an exercise. I think the audience was extremely lucky because this was really getting down to a succinct way of sharing your experiences for their benefit. So thank you so much for joining me in this discussion. Malcolm, would you like to close it as the RefSim owner here?
Thanks, Justin, and thanks, Astrid and Simon. That was an excellent discussion, and it was also very clear that you have barely scratched the surface. There's a lot behind what you were talking about, and I'd like to reiterate that RefSim is working on creating a year-long series on this topic, bringing you these sorts of webinars, recordings, educational videos, and other resources in this very specific area. You'll hear more about this either on LinkedIn or through RefSim directly. Please sign on at RefSim to get the updates on this program, as well as all the other resources that you can find on the site. Justin, thank you very much for hosting this, and I'm sure the audience is going to hear a lot more from all three of you. Thank you, everyone.
Okay, thanks.
Thanks all.
Thank you.